recordings online.
All right. Well, sounds good to me.
Awesome.
Um,
Okay, what do you guys got?
well, as you know, we're working on the trash ejector. And so far, although we do not have a presentation, we do have a prototype.
What I
Awesome.
want to see. That's awesome.
It's just a like quart paint can, stainless
Yeah.
steel. The
Yep.
lid likes to fight me.
Okay.
But our idea is to have the trash ejector have the general layout of door on this side, door on this side. This side is gonna be like a sealed door that they can like open up into space
Okay.
and have the stuff be pushed out into. And another seal, this is the door that they'll open and put stuff into and just set
Okay.
in here.
Okay. That sounds great.
And the way that we plan on getting the trash out is via like refillable or like flexible air bladder attached to the door.
Okay. That's
And
interesting. How do you want to do that?
well, we're hoping to have an air pump, like have some tubes running into the door, like preferably like from around the hinge area, so it's not bulky and in the way. And so it can just fill up and like deflate the air bladder whenever it wants.
Okay, what's that? Oh, that looks like a peristaltic pump.
Yes.
Okay. And do you think you need a pump?
Yes, to get all the air out of the
Yeah.
trash ejector before they open up the door.
Very good. Okay. So part of what I'm asking is if you use that pump to suck air out and then you open up the outside hatch, the the bladder that you want to put inside will get filled up by air pressure inside the spacecraft, just pumping it up all on its own.
True. I didn't think of that. Pressure difference.
We did not. I did not either.
Huh.
I completely spaced that too.
Does that make sense?
Yeah, that actually helps a lot. We completely forgot about that.
So, I like your idea, and part of what I like about it is that you're not losing air, right? You can use air pressure to push it out as long as you don't lose the air, and that's a good method of doing it. Okay, so how do you want to demonstrate this?
Well, right now we're going through an issue with the pump being attached to the thing itself because unfortunately the tube that we got is too small to attach to the pump.
Okay,
Use it eventually.
We are waiting for a new tubing to come in, but
hold on. What do you mean? Show me what how you're trying to do it.
so we have a one-way valve attached to
Okay,
the tubes that's attached to the prototype.
okay,
And the one-way valve too large to connect to the pump.
to that tubing.
Yes. And so we're hoping to either get like new tubing, different pump, or a new smaller one-way valve.
Well, all you really need is some kind of an adapter, right?
Yeah.
Okay, let me see if I can help. Where'd it go? Yeah. I'm looking for a syringe.
That might work.
That was what I was gonna propose.
So I have a big syringe, but I bet you guys have different syringes at home.
Yeah.
Okay. And what I'm thinking about is your on the place where you could put a needle, there's a small nipple, right? And then depending on which kind you get, you have a larger one on the opposite side. Does that make sense?
Yes.
And so I think that you might be able to cut off, like take an old syringe, cut off some of those other pieces and or some of the other things, and be able to have an adapter right there. Does that make sense?
Yeah, it makes sense to me.
Um, Another option, you could take both your hose and your pump over to the hardware store and show them to the hardware store person and say, I need to connect these. Do you have an adapter? And I have $100 that says they do.
Okay.
I think that you can find that adapter and it won't be all that difficult. At first, they're going to hand you a brass one. Ask them if they have a plastic version. Okay.
Yeah.
I think you can do that. Okay. Show me more about what you've got there and what you're thinking about.
All right. Well, the next thing we're thinking about right now, unfortunately, we don't have too much to show for this idea, but
That's
it's
okay.
for the hinges
Yeah.
for this door.
Yeah.
Because right now, we looked around and there's no like commercially available like solid hinge for something round like this and like
Well, wait a minute. Come on. Hold on. Okay. And you're right. There's some difficulty because it's round. Okay. But you can imagine here, this one would not work. It's way too big. But part of the difficulty is that it's also very flat. Now, if I have it narrow, it doesn't matter if it's on a round surface or not. This side would probably work for your for the rounded side of the can, and then this part could work for the flat part of your can. Does that make sense?
Yeah, but the thing we were considering is because this paint can is like a little protruded and it needs to lift up before it can be pulled out.
Don't worry about that.
Okay.
Right now, I am not so worried about you guys getting a good seal as much as I want you to show as much of your idea as you can. Does that
Okay.
make sense?
Yeah.
Yeah.
So show me how it works, and then later on we'll talk about getting it to seal. Because some people are using 3D printed things, some of them it is hard to get something to seal like that. Okay? So
Yeah.
don't worry about that. Now tell me about the other side. What do you want to do there?
Well, we were hoping to have like a mechanically or like maybe even button press like activated door so it's like easy to just press a button and have it all get pressed out.
Sure.
And we're hoping to have it just like we aren't entirely sure about like the door design or whatever. It could like open up like that or just
Uh-huh.
one-sided. But whatever it is, we were hoping to make it like first off a little thicker than just paint can since
Sure.
insulation, whatever, so on and so forth. Not the important part, but we're also trying to find like and think about what would possibly be like the least like bulky and easiest form to get that fitting on the outside of an air like spacecraft.
Sure. Okay. So I have some more examples. All right. So this is a 3-inch PVC pipe.
Yeah.
Okay. And notice how nicely the can fits inside. You see what I
Okay.
mean?
Yeah.
Now, and so you can imagine that you can do a door that opens like this, right? You
Yeah.
can do a door that opens like this,
Yeah.
okay? And you can do a door that opens like this, right? Now, could there be other ones? Probably, but those are the three I can think of, okay? And so if you guys go to a construction site, you might find some pipe, right? And ask them, hey, I see this is in the trash can. Can I have it? And they'll say, oh, yeah, go ahead. Or you go to the hardware store and say, do you guys have any leftovers? Because sometimes they'll cut stuff off and then they'll have pieces left over. Sometimes they'll throw them away, and other times they'll sell them to you for a cheap price. Okay. So look for things that are cheap. I really like to build my prototypes on free or cheap whenever I can. Okay. So now you can imagine if I have a door that opens like this, I have to have a pin that it pivots around, right?
Yeah.
Okay. So that means from the inside, all I'd have to do is have a handle so that I could pivot that. Does that make sense?
Yeah, it does.
So, and another option is if I can make a handle on there that pivots, that means that I could also put a gear on there and I could use a motor if I want.
Yeah.
Now, it's not a requirement to have a motor, just so you know that the windows on the space station, they're all hand crank to be able to open up the outside They've got like a shield that they open up. Okay, so don't think that you have to use motors.
Mhm.
And can you? All right. So now, how did you say you wanted to? Oh, we wanted to use an air bladder. What kind of air bladder do you think you want to use?
Well, we were having like an issue finding like good materials for that were like, space worthy and flexible.
Do you think we need space worthy yet?
No, 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 no. But
No.
thinking for like the prototype, we were thinking about just using like some form of like maybe even a sandwich bag for the first
What
test.
about a balloon?
Huh?
What about a balloon?
Oh, balloons. Okay.
We talked
Yeah.
Oh my
about
gosh, right? Okay, so imagine you take a balloon and you want to protect it because if you're going to do this over and over, you're probably going to scratch it up if you
Yeah.
have it rubbing against your can or something like that, right? So what if you put like take a piece of old t-shirt, wrap it around your balloon, and now you can either you can have a pump or you for demonstration purposes you go, and the whole thing just blows up and it pushes your can out. Does that make sense?
Yeah.
No, I think you guys have a great idea. I think that you could do that without too much trouble. Now, consider so um so you put the can in, you close your inside door, right?
Yes.
Then before you open your outside door, you use your pump to suck the air out, right?
Yeah.
Okay. As soon as you start sucking air out, that bladder is going to expand out and start pushing on your can, right?
Yeah.
So what do we do on that door with that bladder to keep it from blowing up right away, from
Oh.
inflating?
What could we do? I mean, what do you think, Gabe?
put a lock.
A lock?
Yeah, do like a simple like catch lock.
So like a little valve, right?
Oh yeah. Okay, yeah.
And it can be a hand valve, right? So put a valve on the door that goes to your inside bladder, right?
Yeah.
Now, what you can do is can you find a valve that's similar size so you can use some kind of a hand pump to demonstrate that portion?
Yeah.
I bet you could. And that's also something that's at the hardware store and say, hey, what kind of valves could I use? And it'll probably be a water valve. Is that okay for using for
Yeah.
air? Yeah, sure. A valve is a valve. So I think, um, so again, let me start from the beginning. I slide the can in, I close the door. I start pumping out the air, and then I open the outside hatch. Once I open the outside hatch, I open the valve from the inside, it expands the bladder and it pushes it out. Does that make sense?
Yeah, that's sort of exactly what we were going for.
Yeah. So I think you guys could do that without too much trouble. And it's a great way to demonstrate just because you're not losing air. Now, asked, is it going to inflate?
I'm sorry. Can you repeat that?
Cut out of that.
How fast is that bladder going to inflate to push your can out?
Well, I guess that would be dependent upon how large the valve is.
That's exactly right. Okay. So it's a matter of how fast you open that would help determine how quick it's going to be ejected. Does that make sense?
Yes.
Yes.
Okay. All right. Um, if it ah, what if it expands slowly, but I have something here to keep it from getting kicked out right away?
Oh, so it builds up pressure.
Yeah, let it build up some pressure. And then once it gets to where you want it, you flip that little trigger and now it gets pushed out.
Yeah, that sounds like a great
You could
idea.
do like a net.
That was like a
Yeah.
submarine thing.
Yeah.
Big up on the submarine.
Does that work for you guys?
Yeah.
All right. I think you guys have something that's kind of fun. Now, so do you need to stay with that paint can?
No.
Not necessarily.
I don't know if I'd stay with the paint can because I think it's a little bit small it doesn't give you very much room to play with. And it's awfully thin. And I don't know about you guys, but I'd probably ding it up myself. Just because you open it up, you cut off that side, and now it gets dropped and it's all bent out of shape and everything. So you might look for something a little bit bigger, whether it's a piece of pipe like what I've got, or you could do that. There's probably other cylindrical containers, right? I think a 2-liter bottle is probably too flimsy.
Yeah.
Do like
But I think there's other kind of containers that might work like that.
What
Does that
about
make sense?
Yeah.
Too big.
Yeah, I would like you to use a container that you could see what's going on in the inside.
Oh, okay. Yeah.
That
That's
might be real
great idea.
important for you guys.
Actually, somebody else was talking about using some Lexan for one of the doors, and I
Yeah.
thought, that's actually a really smart move, just because when the astronauts are firing trash out on a regular basis, you can imagine that there's going to be a day when something gets in there that's not supposed to be. And, it jams up the workings. And if you've got visibility inside, it means you can figure out how to solve the problem. You know what I mean?
Yeah.
Yeah. Yeah,
And so
yeah.
transparency, even just a window or something like that, I think has a lot of value related to this thing. So,
Right.
anyway, all right. You guys got any other thoughts or questions?
Questions?
Well, man.
mm,
I think we're good.
All right. All right. I
All
noticed
right.
your Johnny Cash shirt. Are you a big fan of Johnny Cash, or is it just a shirt?
I like some of his songs.
Me too.
Yeah.
My wife just recently went to the Johnny Cash Museum in Nashville.
Mhm.
And I thought, I'm not a big fan. I like several songs, but it's not quite the same as Elvis for me. You know what I mean? So, but they were good buddies too. So, anyways, all right,
All
guys.
right.
Thanks a
Thank
lot.
you so much and happy holidays.
Happy
Um,
holidays.
Thank you for your time and work on that. Actually, Glenn, we have 15 minutes and Laurel is on.
Okay.
Laurel's eating lunch. So
Oh,
Miss Moon can, and I know Chase, who was a student last year, is on that team they're doing the trash ejector.
Okay, sounds
But
good.
they're just beginning.
Okay.
So, Laurel, do you have any questions for us?
Yep, there's somebody there.
Yeah, we see you. They not real well. It's like the room is dark. Oh, there's Chase. Yeah.
Hey,
Hi,
Chase. I can see you. I didn't hear you yet.
Yeah, we don't hear you. And there's Miss Moon.
Hi, Miss Moon. How are you doing? Good to meet you.
I'm so glad Laurel got involved again. They were very late, but they're
trying.
doing it. Yeah. I said I'd do their PDR closer to Christmas.
Okay.
Huh? You know,
There you
that-
go. Oh, we hear you now.
Okay, you can hear us?
Yes.
Okay. I don't think we have any questions so far. We've just begun building a cardboard model before we start 3D printing our parts. So,
Okay.
So
What's your cardboard model look like? It's okay. I've seen a lot of cardboard.
cardboard model is the way you start.
this is our cardboard model. It looks
There
so
you go.
beautiful.
It looks like a rectangle.
It does. It is a rectangle.
It looks like a nanolab. So what are you thinking for how you're gonna do this trash ejector?
So what we had planned is, so you can see on our model. Basically, this would be in the floor. So you open up here, and this is basically a floor compartment.
Sure.
And so your can, I have to go buy chicken noodle, but I have tomato for my example right now. I know. That's gonna go in here this way. My hole's not big enough right now, but
Okay.
it'll go in this way. And the way it will work is we'll have a separate plate that will be in here, loaded by a compression spring. And so that will be ready to be launched at any time, and we'll have something in here holding the plate back. So once we get our garbage in here, no matter the size, say they didn't have as much garbage as they did one day or more, no matter what, that plate will be able to push whatever it is that's in there out using the force from the compression spring that we can release from the inside.
Okay. How would you change? So do you get to change how much compression you do on that spring? How would you do that?
So the way we would be able to do that is we have a cable that so the plate's going to be on rails, and then a cable will hold the plate for like when we need to pull it back, we can just pull the cable. But then
Sure.
also if we wanted to change the amount of force on the plate, we can adjust that using that cable as well.
That sounds good. Okay. I think that's a great beginning. How big do you want to make this thing? I mean, your box seems small, so
Yes.
what do you want to do?
We plan on keeping the actual compartment small because we don't want to have to worry about that air difference. So we're trying to keep it with that 10% of the volume of the can to not have to worry with the air. So that will be relatively small as well. But then I plan on building something around it because we'll have our exterior door, which will be, my plan is to have this modular so this can go in and out. Say they had a problem with it, you could close this exterior door, bring this module out and put another one in.
Okay. So do you want to 3D print everything, or do you have some
it's all
other
going to be
pieces?
3D printed.
And why is that?
It's easiest for me. I've gotten used to 3D modeling quite a bit. And we have two very, very nice 3D printers here at our school, fortunately. So I can print like something this size would take just about 2 hours probably.
Look at Glenn.
So this is
hold on, I gotta make you bigger. There we go.
See, so what I'm suggesting is not everything needs to be 3D printed. You might be able to actually move faster if you use some other materials. So for example, here I've got a deluxe mixed unsalted nuts, right? Okay.
Yeah.
And so it's a big enough box that I could do a lot of things with it. Does that make sense?
Yeah.
Here's another option. All right. So I got a piece of PVC pipe. This is a 3-inch PVC pipe, and I got this for free. I think it was at a construction site, and I said, "Hey, you guys need that?" And they said, "No, take it out of here." Right. And so with that, it's actually about a 1/4 inch thick, which means that I can use a lot of screws and things like that as well.
Yeah.
For whether I want to put a door on it that opens out like this,
yeah,
or one that swivels, or one that slides. You see what I mean?
Yeah.
Now, making a side door like what you're talking about, yes, I got to use a saw for it, but it's
that's doable. Yeah.
You see what I mean?
Yeah.
So, anyways, I just wanted to offer you some other options because I love 3D printing. There are certain things that I can't do unless I 3D print. But then there's other things where it's like a pipe. It's so much quicker for me to go get a pipe, right?
Yeah.
And the other thing is when I know that my 3D printer does not work every day, right?
Yeah.
And especially if I'm wrestling with somebody else, sometimes there's just so many things getting printed, I don't get my time. So just things to consider. You might find some things are very specific, like maybe the door that you want on top, print that, right?
Yeah.
But then if you can use a piece of pipe or a piece of recycled container or something like that, sometimes that just makes you go faster. Okay?
Yeah. Sounds good.
So what I was thinking, Chase, is what you could do is instead of building your whole tube, just build the important part. Like like an inch of the lid so you can see how your lid and hatch works, and do the bottom. So the important part isn't in between these two, it's the top and the bottom.
Yeah.
To demonstrate what you want. And once you got the top and bottom 3D printed right, then you could go to a whole thing if you want.
Yeah.
That's good thinking. Oh, what about your springs? Do you already have your springs?
No, I was gonna run to Ace Hardware. The nice thing is my partner, who's not here today, he's wrestling in Sydney. He works at the Ace, so we get a pretty good discount. So we looked, and they had like a 3/4 inch compression spring. So we were just gonna pick that up.
I think that's
if you go to the Ace Hardware there in Laurel and tell them you work for the NASA Hunch, they used to always give it to free or a really good discount. So just tell them what you're doing. that was actually, now when I'm thinking about it, is 20 years ago. But they used to always do that.
That's terrific. Yeah. And by the way, Ace Hardware has a really good set of springs. So don't just go in and say, this is the one I want.
Yeah. Tell me your selection.
Yeah. They've got a lot of different types of springs in there, and that'll help you out a lot. Okay? All right.
Yeah.
Terrific. Very good to meet you.
Yeah,
Yeah, he did the robot last year, right?
Oh, did he? That's great.
Yes. I began that, and we didn't get too far too fast, but
okay. Well, see how far you get this time.
This is a lot less complex, so I think we'll be good.
Okay. All right. We'll see you later.
Thank you.
Yeah.
And you can see I'm actually having it loaded right now onto our NASA Hunch YouTube. I have a special playlist that if you go to that playlist, it says 2025 PDRs. You'll see there's probably at least 20, maybe even more.
Oh, there's a lot of great ideas. And so being able to watch some of those videos could be helpful. Okay.
Yeah.
Thank you.
All right. We'll see you later.
Okay.
Bye.
All right. So we're waiting for our last school.
Is it just Billings?
No. Victoria Park Collegiate Institute.
Oh, okay.
In Canada.
Yeah, that's terrific.
And they should be coming on any minute. Their thing is 12:45 and it's 12:40.
Sounds good. I'll take a break for a second.
Yeah, and I'll pause. Introduce yourselves and then tell us about your project, please.
Okay.
So hi guys, I'm Devesh.
I'm Gujarat.
I'm Nemo.
My name is
And I'm Darshni.
Oh, awesome.
Yeah, so we're actually working on the crash ejected system for this year's NASA Hunch PDR. And should we just jump straight into the presentation, or?
Sure.
That's fine.
Okay.
However you want to do it.
Yeah, I was gonna share our screen. We made like a small presentation for you guys.
Terrific.
It's coming on. There it is.
NASA trash ejector. Hey, you got both moons in that picture. That's interesting. Phobos and Deimos.
Yeah.
Oh, okay, yeah. So let's go straight in. So we're going to be looking at, so we already met the team, and we're actually going to be looking at our design process, what ideas we came up with, and what type of designs we came up with. We drew it out, and some of them we modeled it, and then we actually had like deep discussions on why we chose it or why we didn't choose it. And then we're also going to be talking about what we learned with each design. So yeah, that's what we're going to do. And then we're going to also talk about current design and then hopefully get some feedback from you guys. And we also have some questions for you guys because we didn't understand some parts of it. And yeah, so that's what we're going to be doing today. And yeah, this is our little introduction.
Okay. So I'm gonna be talking about our first prototype. When we worked on our first prototype, what we discussed was that we want to keep it really simple. We want to keep the design pretty simple. So for the first prototype, what we really went with is just a general feel of how we are going to make the trash ejector. So here in the diagram, you can see that we have a side view and a front view. So essentially what we just thought is it's just going to be a modular component that ejects trash somewhere. And for the first design, what we went with is we went for a design that focuses on sealing the hatch, which is shown in the picture with the front hatch and the back hatch. And for this design, we went with buttons that could control the front and back hatch and a button to obviously eject the trash, and then um, a, a computerized system to prevent you from opening both the back front and back hatch at the same time to prevent air from escaping. And what we liked about this was that it was simple, and the idea of a hatch worked pretty well to seal the air. However, what we didn't like was that we didn't really find any solution for to generate rotational energy when the can actually goes out of the space station, because obviously we want rotational energy to create that extra stability when it goes out so it doesn't go flying randomly. Um, and just as another descriptor that I forgot is that although not shown in the image, this design goes with a spring system where we load a spring prior to putting the trash in. And then when we press the button to eject the trash, the spring system uncoils and then it propels the trash forward. However, what we didn't like about this is that it's hard to implement. Again, as I said earlier, our main goal of our trash ejector is simplicity. That is our general theme of the trash ejector. We want to keep it simple. And we felt like a spring system wouldn't be simple enough. It would be too hard to implement because there are sources of error, including the spring system accidentally popping, or like the spring system not loading up properly, which can hinder the performance of the actual ejector. And also we just wanted to go with something simpler to implement and simpler to understand for the crew that is going to be using our ejector.
Prototype, it was to use the electromagnetic system, which is inspired by the magnet train. So basically, the magnetic ring would be attached to the motor, and the motor would be attached to a piece of metal in the back of the soup can, and that could spin, right? So we use the electromagnet to spin the motor we also use it to minimize the air resistance and the vacuum effects. The advantages were that it provided a complete airlock and there was less air resistance. But one of the main disadvantages was that due to the magnetic field, it could affect the other tech in the space station. And as we said before, our main theme was to keep it simple. So this was really hard to implement and it was not very practical because of the complex setup. So we would learn that electromagnets are not like really effective and that we try to stick with the idea of being simple.
So here's a third idea that we had for the ejector that we thought was pretty interesting. Is inspired by the barbershop sort of optical illusion where the pole is spinning, but it looks like the rings are perpetually going down.
Yeah.
And we can apply that idea to the gears where if the gears are spinning and the teeth are angled at a certain way, we can transfer that rotational motion into linear motion. So we had that idea of having the motor spinning in perpendicular to the uh, direction we'd be ejecting, and then using this principle to change this rotational motion into the linear ejection. The While the idea was interesting, we found that it was complex, and also in addition to being complex, it was almost needlessly complex that it really gave us no additional benefit to what our current design is today. But we thought it was an interesting idea, and it would, well, one of the benefits would be that it would save on some space and would add some stability if we implemented it in the way that um, we drew out. But it's a little bit too complex for the little benefit that we would have compared to our current design.
Okay.
Yeah, just for FYI, this is for our linear like system that would move the trash eject out and in, because that's what we're trying to use this gear system for. But yeah, and
Yeah, that brings us to the current.
yeah, so this brings us to our current design. Okay. Oh, go back.
All right. So as for our current design that we plan to implement is it's sort of this crankshaft arm that you can see on the left. It's sort of a rough 3D model, but I think it sort of portrays the idea in which we're trying to accomplish. So as you can see here, this blue arm is going to be powered by a sort of a servo, and the servo is going to push the slider back and forth, which our trash will be attached to, and this trash will be able to be ejected by the sort of crank arm mechanism. So our casing will sort of look like this, and we're gonna have a protrusion in our base, as you can see in the bottom, and our slider is gonna be resting on top of this protrusion, and the crank arm will be able to pull the slider back and forth. So now I'll hand it over to Devesh to sort of show our 3D model and sort of our to scale model.
Yeah, so this is just like a picture of what this would look like, hopefully in the final product. And just a quick, so this is going to be our model. So yeah, right here, this piece here would be a nine. We're using a 30 kilogram servo, uh, and this would be our trash, like our actual trash can. And this here would be a DC motor. What we're going to use this for is to spin it so that there's a proper projectile motion when it leaves the space station. Uh, yeah, I just want to move on over to the our actual 3D model because that's oh. So yeah, this is our simulation kind a model. So you can actually yeah, right here. So um, right here, this is what we were thinking of actually building. So currently it's a model, but basically this servo here would, as Gajanan just talked about, this small crank arm would be connected to a servo, and we would push it like such. And of course there'll be a DC motor. We're just using a blocks to show it, but there would be a DC motor spinning this hex piece over here, which was then connected to our trash can, and I can actually show you how that's being Um, right here. So this is how these are our separate pieces. So yeah, this is our trash can. Our trash can at the back would have like a part for it to be for it to be connected to the DC motor setup. So yeah, I just wanted to show you guys that. Um, oh,
So that's an interesting idea.
yeah.
So how did you want to put that on your can?
Right. So so our can will have so this hex piece here would be connected directly to the DC motor, and as I showed you before, like that opening there on the bottom of our trash can, that's how it's going to be connected, like such, like over right here.
Sure.
And what
I
we're
mean,
hoping for, yeah.
and what I mean is you don't want to damage the can, right? So that's part of a requirement right now is you can't you've got to have a can that's full of the soup. Okay. However, it's okay for you to make something that attaches to your can. Is that
Yeah.
okay? And
Okay.
so I think what you could do is make a like a little cap that fits on the bottom of your can, right? So here's your can, and you can make a cap that fits on there that would have the indentation that you need. Does that make sense?
Yeah, so that was actually going to show you that we've a model for that as well. So this would be a small piece that would actually connect. So we were brainstorming different ideas, and one of it was this type of model here. So this would actually go onto the our soup can. But our actual question that we actually had for you guys was, uh, we talked about how we wanted to maintain a space vacuum inside this whole system, right? And for that, we designed a model where we'd have a garage door design. Go back to the presentation here. So right here, our goal was that. Oh yeah. Um, what we were trying to accomplish was that once this crank arm was all the way to the end, this part here would be covered by the our piece, like our cap, right? So that it's actually filled in, and we were trying to have like no space in between so that no air actually goes out. And we'd have like a small garage door design. So for example, there'd be a garage door, it goes up, and then you push the trash out, and then you close the, I mean, yeah, and you close it, and then this comes back out so that there's no like open space basically.
Sure.
But then later we realized that that wouldn't really be feasible because even those tiny gaps could cause the air to rush out. So I just had a small question. So do you think that this would be like a possible, I don't know, like would this work, or should we use something to suck out all the air? So depressurize the room and then
Right. And so we don't want, every time we throw out trash, we do not want to lose that volume of air, because that means that we're decreasing our air for the habitat, right? Our air for the spacecraft. So you've got two holes there. You could use one to suck out air just before you open up the outdoor hatch, right?
Yeah.
And then once you've ejected the trash, you close the outside hatch, and then you let air in again so that you can put a new can in. Does that make sense?
Yeah. So yeah, that's what we didn't know because we added the holes for that purpose. And then we were thinking, okay, maybe we don't need to do it if we can make our system so perfect that there'd be no gaps. But I don't think that'd be feasible. So yeah.
But
So
in actuality, if you that little lip that you're adding to your can,
yeah.
right? If you designed it so it didn't go outside your door, that it had a ridge around it, that it would stay inside. The can would go out, right?
Yeah.
But it would stay inside. The air pressure in your ejector would keep that little part that you 3D printed against the door, and because of the air pressure, the air would be trying to push it out, and there's a vacuum outside, so it would stay really tight against that door.
Yeah, so that was exactly our plan. But so would that work? Would that be fine? Because that was exactly our plan. We were gonna have like a piece, and the other piece I showed you, the cap or the so this piece would actually go against that wall and hold it, and then our actual soup can would be attached to these holes and then be pushed out to here. It'd be a little bit closer. So this would actually close that hole, the opening.
Right, because it wouldn't be outside.
Yes.
Right.
Do you think that will work, Glenn?
Yeah, so it's kind of like in a syringe, right? So you'd have to have some kind of a sealed piston, like what and I can't, oh, there it is. Okay, so if you've got a syringe, right? This one has like 3 little gaskets in there that are keeping the seal. So you could make it so that as you push the can out, as long as you don't lose, as long as you've got a good seal there, you're not going to lose the air, and that works fine.
Okay.
Do you need a motor if you've already got an air seal?
We were hoping to, get rid of that whole depressurize process and maybe, make it more faster or like make it more cost efficient. But again, do we still need it if we have a perfect seal?
Well, consider if the tip right here is open to the air pressure of the spacecraft, right? When you open up the hatch, or excuse me, let me back up. So you suck out any air that's in here, right? and then you
Right.
open up your hatch. This is all vacuum.
Right, right. Yeah.
This is at 1 PS or one atmosphere. There's plenty of force there to push this out.
Yeah,
You
that
see
makes sense. Yeah.
So you could use, as long as you're not losing atmosphere,
Mhm.
you can use the air from the space station to push it out.
So you're saying they don't need the blue and orange pusher?
Potentially. I mean, if they want to work at having a sealed thing, then why would I bother with the motor if I could use the air pressure from the space station? But that means that you have to have, a really good seal like this, right?
Yeah.
Now, if you want to go with your motor idea, I'm okay with that as well. But I wouldn't bother with trying to get everything to seal because there's no purpose.
Yeah, okay. Another question is that if we were using this motorless design where we use the air pressure from the space station or whatever, would that be because we're technically losing the cabin's air pressure, right? That wouldn't be good for the actual cabin though, right? So we should probably
Correct.
use right. So it's better to use a motor design and where we don't lose any air pressure.
Yeah, you can do it either way as long
Okay.
as you don't lose air pressure.
Okay.
Now, one thing, so on your design that I see right here, when you pull that all the way back, where does that arm go?
Right. So we're actually gonna make the housing a little bit like our housing would go till here. So it's gonna be a little bit bigger. It would go all the way back. It would go behind the motor, actually.
Right. Okay.
Yeah.
And part of what I'm asking is, you're extending how big your canister has to be. And so part of my question is, can you change that mechanism a little bit so that it doesn't take up all that much space behind it?
Uh,
That was kind of what we were hoping to do with the
Oh, hold on a second. Hold on. I might have one.
can we full screen it? No, you're just pinning it. That's not great. It's fine.
Like,
If you pull the corner, you can.
what is?
No, the bottom.
Oh,
I thought you were taking computer.
No. Sorry, I was looking for something and didn't find it. Okay, keep going. Tell me what you're thinking. I interrupted you.
So could you go back to the slide? So that was kind of an idea that we were that's kind of the idea that we had when we came up with the idea for the slanted gear, the diagonal gears and the barbershop pole idea. So which side was it? This one, right? So the idea here is that the plastic hold sort of the plastic that we print to hold it would actually be a lot like it would go back a lot less and it would actually just overlap with the motor instead of going past the motor. So that's sort of the idea we had here.
Could you guys stop sharing for just a second and I'll share?
yeah.
Can you guys see that?
Yes.
Okay, so do you see so here I've got a boxing glove, and here's the mechanism that extends it, right?
Mhm.
Would that help you guys?
Yep. So we did consider this type of design. We looked at it. And then we thought that, there's gonna be a spring. Again, this is sort of similar to our spring idea where you have to pull it back each time. And we were thinking maybe using ropes and all of that. And then we thought that, using a motor would be like easier and more efficient. We thought because this could like this way, yeah, like our design here, we thought this, like our final design, we thought it'd be more consistent. We did actually consider this a very similar design where like a gun would pop out or something. But again, we had to use a rope or something to pull it back each time. And we didn't
Why is
really
that?
for it to come back and then be, shot again.
Oh, no, the idea is that our original idea was that the spring would be the one ejecting the thing, but if I understand the other mechanism correctly, the spring is actually to pull it back. Is that and then
You choose which way you want it to go, right? So
Yeah.
you can have a spring that pushes it out, or you can choose a spring to pull it back in. It's either way.
Yeah, so for the X mechanism that they just showed, it has the spring pulling it back, and then you push the button to push it out.
Oh, okay.
Against the spring.
Yeah.
The idea was that any way we did it, where the spring is pushing out or the spring is pulling back, we're going to be working against the spring in one way or another, either by pulling it back if it's pushing out, or pushing it out when the spring is trying to pull it back. And we thought that this would be if I understand correctly, it would be less consistent over the long run, and that's why we sort of moved away from springs.
Yeah, we also thought more main. Yeah, we didn't really like that idea much.
But do you have to use a spring?
Sorry?
Do you have to use a spring? I mean, can you move that with a motor?
Maybe
If
like
you
a
have a motor,
we could use that
you
as a
can
scaffold.
push it out or you can push it in with the motor.
Yeah. Also, we were also another factor was I'm not sure if it's a requirement, but I read on the PDF it had to spin as it got out the space station.
It's not a requirement. It's
Right,
an
but it's an option. Okay.
But what Glenn showed you, it's just don't use a spring, just it shortens your blue and orange
linkage
thing, the linkage, right? Thank you, Glenn. It just shortens it so it doesn't stick out as much at the end. Still keep with your design, but make it in 5 little linkage instead of 2 is what he's saying.
And if you look at the if you look at that model of the Skylab the Skylab trash ejector in the presentation, you'll see that it used this same kind of thing. Now they did it with a hand mechanism, and so it was just it was a lever that they would move back and forth. Now, if you want to do that with a motor, you could do that same thing with a motor if you wanted. Does that make sense?
Yeah.
And all I'm trying to do is look for a way to kind of shrink up your linkage so you didn't have something trying to poke out the other side. Okay?
Okay. All right. Yeah, that makes sense.
I have a question about if we did decide to go down this the idea of using the air pressure to push out.
Sure.
I understand that for our model, for CDR, we don't have to have it airtight or anything. We just had to show that it could be airtight. So
that's right.
For our design, I'm just imagining that I don't think we want to show up to CDR with just like a box and then saying, oh, the vacuum will do the rest. So do you have any suggestions for bringing a practical model, like having that sort of representation of using air pressure without having to do like it being airtight and perfect?
Sure. Well, and you can choose how much of it needs to be airtight, right? So, for example, I've got this pipe. This pipe would be relatively easy to do something where I had air pressure. Now, so for example, what did I do with that thing? Where did I lose it? There. Okay. So for example, on this one, I've got all the airtight that I need right there, right? So for example, if I slide this into the pipe, and then I have a valve over here on this, right? So let's pretend I do it this way. Let me set it up so that you guys can see what I'm thinking. So here's this. I would slide this in from the top, maybe, right? And then I would open up my door, right? And then I would let pressure in from here, and it would push the can out just because of the air pressure inside that tube. Does that make sense?
Yeah.
Yeah.
Now, and don't pretend like that's the only way to do it. There's 100 ways to do it. So, for example, you can 3D print a door here. Now, does your door do this? Does your door do this? Or does your door do this? You see what I mean?
Yeah.
And then what do I want to do on this side? Do I want to have a door that does this? Does it do this? Right? Or does it do that? Same kind of thing. Okay. And then, or do I want a door on this side at all? Right? It might be that my mechanism for pushing it out is all right here, and I put my trash can goes in from the top. But then I have to decide, how do I want this door to work as well? Does that make sense?
Yeah.
Okay. So, and don't let me lean you too far in the direction that I'm talking about, right? The idea that you guys have works just fine. Okay. If you want to use motors in there to push it out, I'm all for it. That's just fine. If you want to use the linkage that you have because there's a reason why why the way you see it to work, stay with that idea. Don't switch over to what I'm saying just because I have a boxing glove from, those old movies or something, right? You guys can do it any way you like. Okay. I think that what you've got is very workable. It's just a matter of how do you guys want to manipulate and solve some of those problems. Okay?
Okay. All right. Yeah, that makes sense. We're gonna yeah we also like the idea of the using pressure to push it out. So we're gonna maybe try to figure out how that we could work that out and how we could show that.
Sure.
If not, then we're probably just gonna use our linkage system and try to make it smaller or try to not have it go back too much.
Yeah, by linking multiple.
Yeah, we're probably gonna
have. Didn't we do that for robotics for that one time? Do you remember? The X.
Oh, we did do that.
The X.
Yeah, we did something similar, but with like a scaffold design instead of
Yeah,
the
yeah.
linkage. Yeah,
I think that's a great idea. Okay, so and now one of the things that's important there is I've got this door. You can't go outside to open it. How do you want to open it?
Electronic.
Well, we were gonna use an Arduino or electronically, like with some sort of a system for that.
I'm okay with that.
Yeah.
I mean, do you have a mechanism for how you want to move that door?
Yeah, so our current design, what we thought of was a garage door system. What we were thinking of before this whole
Yeah, you
vacuum.
said garage door. Okay.
Yeah. So what we were thinking of was that garage door is closed. Our can comes in, put full seal, right? So there's no no air going in. So full seal. The garage door opens, trash can moves out slowly and then goes out. And there's still that seal because the back plate's still there. And then garage door comes down, full seal at the bottom again, and then our mechanism goes back. So we were thinking, yeah, with that design, like there's no air going in or coming out, but we're still probably gonna add like maybe a pressurizing and depressurizing system.
I'm wondering.
Okay. And so consider now there's a couple of different styles of garage door, right?
Mhm.
Now, my garage door has brakes in it so that it kind of curves as it comes in. Okay.
Yeah.
But of course, that means that I have more places where I could lose air, right?
Yeah.
There's also solid doors where they move up and get out of the way. And that means that I only have one set of gaskets to have to keep the air in, right?
Yeah.
And so now the question is, though, how are you going to move that you said an Arduino, how do you want to move that door?
We were thinking two DC motors again on each side, and then or one, hopefully one. Again, a DC motor that spins it. We're still working on the exact model for that, but we have an idea or a design in mind. We just haven't CAD'd it yet. But basically, a DC motor again, the motor would spin. We're gonna have an offset so it doesn't, go too much and break the system. So yeah.
Okay. And so if you're thinking of a garage door, that's fine. Go out and look at how that garage door moves to see how you might use your motor, right? So for example, my garage door, I have a remote control for it, and there's one motor that pulls the whole thing up, and then it has a spring that really does the pulling down. The motor is spinning when it's going down, but it's really just assisting the go down. Does that make sense?
Yeah, so it doesn't go down and fall. Yeah, yeah, that makes
That's
sense.
right. It's trying to prevent the garage door from slamming is what it's
Yeah,
doing.
yeah.
That's mostly in a spring. Okay.
Mhm.
So these are just thoughts for you. I think the idea of making it like a garage door works just fine. There's, there's probably 20 different ways to make this. So I like what you're doing. Keep going with that. Okay.
Yeah, you're reminding me of my dishwasher door. It also has a spring, and mine, it's broken. And so the door just slams down instead
Oh,
of
wow.
we got duct tape on it to use as a handle to let it down carefully. But can I see your model again? I want to see the part that's sticking out of.
Yeah. Oh, yeah. This is the
Have you
part that sticks
Yeah.
out.
have you guys printed any of
Okay.
these?
So that part is outside of your canister that's going to enclose your thing. And you're thinking of a motor to move it, right?
Yeah, so it's actually gonna be our servo. I think I have it. We have it actually. Which servo? We have the exact servo we're gonna use.
Servo motor. But I'm
Oh,
thinking
okay.
I'm thinking that maybe an astronaut could also manually move it.
Sorry, what?
Yeah.
Oh, like a
Plus it's
shaft?
stick a astronaut on the space station could
Yeah.
actually manually move it if the servo or the electronics don't work. We love redundancy. And so for a fail-safe thing, they could.
Oh, so you're saying that our design could also be used as like a fail-safe.
Yeah,
Sure.
well, because it sticks out so nicely, it might be to your advantage to have a redundancy there, and you can have an astronaut, have an arrow on it and say, push it this way, and it will eject the trash.
Now,
Yeah.
so have you guys printed any of this stuff yet?
So everything here is to scale, but we haven't actually printed anything because we're changing it almost every single day. But
Sure.
everything here is to scale, so we can print it any day. Yeah.
No, I think that's great. And I think what you want to do is start printing some of it just so you can see, how do things fit together, and kind of play with it, and then print another one if you can, but if you need to. But I think you guys are on a good path.
Yeah, I like it. It's simple. You really wanted to make it simple, and I understand it, so it's got to be really simple.
Because last year, we had a really complex system,
Yeah.
but I mean, we could have make it work. But if it worked, it would have been really nice. But yeah, so this year, I told my teammates like, me and Leo, we were like we're set on like making it simple and efficient.
Yeah.
So we removed all the fancy stuff. So we try to keep it as simple as possible.
And that's
Yeah.
hard to do. So, it's harder to make something simple than complicated. So, congratulations to you for
Thank
doing
you.
that, team.
So, one question for you on the rail that it's being pushed on.
Yeah.
Do you have anything that keeps it from moving up?
Yeah, so we actually we're gonna have a wheel. So we're still need to work on this, but over here we're thinking of maybe adding like a vacuum wheel sort of system. I think I have. Oh, right here, like kind of a wheel like this, and then these rails here. This would be on this like basically this would be inside the we haven't actually modeled that part yet, but so those wheels would be in here inside of this. So and we can't pull it out.
Well, and part of what I'm asking about is, so because we're in right now you're modeling this for one gravity, right?
Yeah, yeah.
Where the gravity is pulling the can down.
Yeah.
However, at zero gravity, you don't have anything that keeps it from going up. And so you might want to have like a T-bar on the top of that so that the whole thing stays down as opposed to starting to float up. Does that make sense?
Yeah, yeah, that makes sense. Yeah.
Yeah.
Or maybe just on the top of your your ejector container, you have another rail like is on the bottom there holding it. So they're both your can is securely between these two things.
Sure. And part of what you want to think about is, if you do something like that, give yourself quite a bit of room in there so that it doesn't bind up or anything as it's sliding down. Okay?
Yeah, yeah, okay. All right.
I think you guys have some great ideas here. Keep this up.
Yes, thank you for working on that. I appreciate it. Any other questions?
Yeah, I just have one question about sort of the air pressure, I guess.
Sure.
So the idea is that when this pushes out and the garage door is open, we want to have something that's stopping the air from coming out.
Yeah.
Like the seal we designed. But also
as soon as you open that door, it's at vacuum.
Yeah. And when the garage door closes, it's also going to be like ideally airtight. So my question is that once the seal is at the opening and the garage door is closed, would it be difficult for us to then remove the seal to reset for the next for the next trash can?
So I think that's actually I'm glad you're asking. So let's put it in. Let me put it in. Let's pretend. So I'm going to make sure that my outside hatch is closed.
Yeah.
I'm going to open my inside hatch. I'm going to put the trash in, right? I close the hatch, and then I want to suck any air that's left in there out because I don't want to lose any of my air. Then I'm going to push my button or whatever. Oh, wait. So I suck all the air out. Then I open the outside hatch. I push the button or whatever that ejects my trash. Then I close the hatch. Now I want to set up for the next one. So I open up my valve and I let air back in there so that I can open this hatch. Does that make sense?
Yeah.
And now I put in my trash and do it again.
So that valve is important because otherwise you wouldn't be able to open it. So that was a great question.
I actually had another question for the whole using the air pressure. I'm not sure about this, but how does the air pressure system in these stations work? Like, is it just like do you have to refill it every some months or something? How does that work? Like, how is there air pressure in there?
Great question. So the space station is kept at about 1 atmosphere all the time.
Okay.
Now, we do have very small leaks where we're losing air a little bit at a time. And also when we're inhaling and exhaling, we have a process where we are cleaning the carbon dioxide out. Also, when we exhale, we are releasing water vapor, right?
Yeah.
And so my point is as we go through the cycle of cleaning that air, we also lose a little bit of the volume of the air. And so I think somewhere on the order of about once every week or so, we have tanks of nitrogen and tanks of oxygen that we release into the space station so that we keep a consistent air pressure and a specific amount of oxygen on the space station.
Okay, all right, perfect. So I was asking because with our whole using the pressure, because we're actually if we use that pressure design, we'd actually lose air pressure, right, each time we use the trash system. So yeah, so I don't know. I don't know if that would be like super effective again because we're actually
We
losing.
wouldn't be losing any air. The
We
Yeah,
pressure would just go down, but we wouldn't lose any air.
oh
yeah.
okay
You
okay
you
okay
want to, before you open that outside hatch, you want to try to suck out as much of that air as you can
okay
with a vacuum pump.
okay
Okay?
okay okay
And that's how, so like right now, before astronauts go on a spacewalk, they'll close their inside hatch. They have a pump that sucks the air out and puts it back into the space station, and then they open up the hatch to go outside. Does that make sense?
yeah, that makes sense. Yeah, perfect.
Okay.
That's what an airlock does.
Yeah. Excellent. Excellent questions. Any other
Yeah.
thoughts?
Good questions.
Yeah.
Is that it?
Oh yeah.
Okay. Oh, go ahead.
No question, just yeah. Thank you so much for taking your time to be with us here today and listening to our questions and answering them so wonderfully. We've definitely learned a lot from what you guys said, and we appreciate you guys a lot for being here for us.
Terrific.
Well,
All
thank
right.
you.
I look for, send us any emails you have. I'd be glad to answer as best we can. So don't be afraid to send us any emails. Okay.
Yeah. Okay.
Sure.
Thank you.
And
Thank you.
and if you need to have another talk session as well, it's okay. Give me a call and we'll work it out. Okay.
Yeah.
All right.
Awesome.
Perfect. Thank you guys. Thank you so much.
Thank you so
Thank
much.
you.
We'll see you
Happy
soon.
holidays to all of you. Happy holidays. Bye-bye. All right.
So that's our last one today. Is that right?
That is our last